Numbers in chemistry. We deal with numbers in chemistry a lot. Chemistry is a math-based science. For the purpose, though, of this class, we're going to limit the amount of numbers we use, but we are going to talk about them and their importance. So first, when we talk about numbers, we talk about accuracy and precision. The difference, they're very different things. Accuracy is when your value is close to a correct answer. Precision has nothing to do with the correct answer. Precision is if your data set, if you are recording data and it's really close together, that's very precise set of data. But we can also talk about precision in like one number. If you have um, a number that has a lot of digits in it, or what we call significant figures, which we'll get to in a little bit, that has very high precision. So I like this photo with the dartboard because I think it helps you visualize what it is. In this first one, we have low accuracy and low precision. If you're not familiar with darts, darts have to hit the red part in the center. So you can see all three blue darts are not in the center, so none of them are accurate. And then you can see they're not very close together also, so it wasn't very precise. Here in B, they're all very precise because they're close together, but they're not accurate because they're not on the red one. And C, they're all pretty accurate because they're all really close, if not in that red one, but they don't have much precision because they're all spread out. And then in D, they have high accuracy because they're all close, and they have high precision. High accuracy because they're all in the red, and high precision because they're all close together. Now, if you go back to C, if one of those darts was on the red and then the other, like one was at the top and one was at the bottom, so they were all very spread out, that would be low precision, but it would only be high accuracy for one of the darts, not for all three. So it is possible to have high accuracy without them being lumped together. We talk about accuracy as like an individual measurement. You can see over here to the right examples of measurements. So a precise measurement, we see 95.0, 95.1, 95.3. Those are all temperatures that are very close together, even though the true value is 100. 5 degrees off from 100 is not very accurate. So these numbers are precise without being accurate. And then in the second one, we see accurate measurements. If the true value is 1 and we have 1.000 and 0.9999 and 1.002, those are all fairly accurate. Obviously, the first two, because they're closer to 1, is more accurate than that third one. They're also fairly precise. They're really close together. Each number individually has quite a few decimal places, so they're also precise. If we look at balances like scales that we use, this first scale over here that only measures to 1 decimal place, that is less precise than a milligram scale that measures to 3 decimal places. If you look at the milligram scale data and you rounded it all to the 10th place, that first 3, all of them would round there. The 3 in 10.333, the second 3 keeps that first 3 the same. In the second one, the 301, the 1 keeps that 3 the same, and then in the third one, the 3, 4, 6, the 4 keeps the 3 the same. So while these are all very different measurements, if we put that same thing on a decigram scale, they would look like they all had the same mass. So that's why it's important for us to use as many available numbers as we can, as long as we know them with certainty. So that's what we call significant figures. It's every number that's used to express accuracy. So every measurement does have some degree of uncertainty because we always round. As you saw in the previous slide, this 3 here over on the decigram scale is rounded. Well, on the milligram scale, the very last value, the 3, the 0, and the 6 is also rounded, because what if we had a microgram scale or a nanogram scale? So technically all numbers have some degree of uncertainty because that last value, the last digit, is always rounded. The greater number of sig figs, the more precise the measurement is. Again, we said the greater numbers, like the more decimal places it has, the more significant it is. All numbers 1 through 9 are significant. It's the zeros that we're not sure about. So when I said that every measurement has some degree of uncertainty, that is true, and it's usually the last digit, unless that digit is an insignificant 0, which we'll learn about significant or insignificant next. So there's a couple ways to have significant or insignificant zeros. On the left side here, we see numbers with decimals, and the rule for if a value has a decimal in it is that any 0 that's trailing a number is significant if there's a decimal there. So these all these values over here have decimals except for that one right in the middle. But with our first value, 10.000, that has 5 sig figs because all 4 of those zeros are trailing the 1, and then there's a decimal somewhere in that number. If we go down to the second to last one, we have 0.0101. Only 1 0 there is trailing the 1. The other 2 zeros are preceding it, so those are insignificant. They don't count. But the 0 in between the ones and the 1 are all significant, which is why it has 3 sig figs. If we look at numbers without decimals, there's 2 rules to know. First of all, the numbers that are trailing, the zeros that are trailing, are insignificant if there is no decimal. So this first one, 10, if I put a decimal at the end of it, that makes 0 significant. Without a decimal, it's insignificant. So the 0, if it's trailing a number, needs to have a decimal in order to be significant. The only other exception here is 101. If you can see that it's the third one from the bottom, 101, that has 3 sig figs because zeros that are sandwiched between 2 numbers are significant. So 101, it could be 1001, so 1001, both of those zeros would be significant. It could be 1,000,001, so 1,000,001. I don't know if I got enough zeros there, but all of those would be significant as well. So if zeros are sandwiched between 2 numbers, they're considered significant too. So we also add and subtract using sig figs. They have 2 different rules. Rules for adding and subtracting. These numbers are a little skew here in the example because I wanted to line up the decimals. So the answer with proper sig figs should always have the least number of decimal places. You can see my calculator answer was 306.871, but the answer with proper sig figs is 306.9 because if I look at the 2 values, the first one has 3 places after the decimal, and in that second value, it only has 1 place. So I want to round to the last place that they have in common. So that's why we rounded the 8 up to 9, because trailing the 8 was a 7, right? So 306.87, so the 7 rounds the 8 up to a 9. So the calculator answer is 306.871, but with proper sig figs, it would be 306.9. And then multiplying and dividing has a different set of rules. This is least number of total sig figs, so this does not deal with decimal places. If I look at the example here, I have 207. That 0 is significant because it's sandwiched in between the 2 and the 7. So 207 has 3 sig figs. 15, 1 and 5, both of those are significant, so that has 2 sig figs. And 144 has 3 sig figs. So my calculator answer was 21.5625, but with proper sig figs, I want to take the least number I was given. So again, with 207, I was given 3, with 15, I was given 2, with 144, I was given 3, so 2 is my least amount. So I'm going to take that 21.5625 and round it to the first 2 sig figs. So 21 is my first 2 sig figs, but the 5 is going to round that 1 up to a 2, which is why with proper sig figs, I have my answer is 22. All right, that's it. Thank you.